once it's off its orbital, now it's going on a circuit like this, and it's going to want to come back to its other ion. So in this circuit, that's where you actually get all your work done. This is where all your wattage, all your voltage, all your amperage is going to go.
Okay, so the way I'm understanding it, usually when you have, say, phosphorus and boron with one another and they're in close proximity, they could be sharing an electron where it's spending some time sharing between the boron, some time sharing with the phosphorus.
So they react together normally, but the silicon keeps them from properly reacting and forming a molecule.
Right.
Instead, it makes the electron basically keep shuffling, creating current.
Yeah, well, they've got kind of an equilibrium there. Then a photon comes in, knocks that equilibrium off, makes it stick more time to the boron, which kicks its electrons that it would normally have out, and makes them go around and utilize that energy. And essentially, it's the energy from that photon coming in that's being displaced around the circuit.
And these particles all lie so that they're aligned so that the electron always goes in one direction?
No.
No, they don't have to be. Basically, what happens is you have one chemical on one side, and then you have one chemical on the other side. So if you look on these are kind of fragile.
So be careful.
Kind of fragile.
So on the front, you see they're really like this.
Okay.
Yeah.
And that's basically because it's silicon that's been doped with another chemical. And I'm pretty sure that the front is doped with phosphorus. So your front side is going to be your negatively charged side. And then on the back, you have this gray side, and that's going to be your boron, right?
And it's, sorry to jump in. The fluorescent lights are normally the inside of the glass itself is covered in a phosphorus coating, which is what actually makes your visible spectrum light. If you don't have that white powder inside of those tubes, if you've ever broken them, you can just see powder fall off of it and there's clear glass. Normally, those tubes just make infrared light or ultraviolet light. And then that ultraviolet light hits the phosphorus, and rather than being captured and turned into electrical current, it's reabsorbing into the phosphorus. The phosphorus itself fluoresces as a white light, and it's not the actual electricity that drives the white light. It's the white light, or it's the ultraviolet light hitting the phosphorus, making a chemical reaction, and re-emitting as a visible spectrum light.
So this is that in reverse?
Similar. Yeah. It's the reason why they have to use phosphorus for that, because phosphorus is very sensitive to light.
Touching is a super reactive, right there.
It likes to give away electrons in something like that.
Yes. But if you look on the cell, so you basically have your phosphorus dope side, and then in the middle, you'll see that white line. And that white line is actually where you connect the wire. So if you look on these, going down these two parts right here, these are where I actually connected the wires, and then on the back side there's also another pin where you solder your connection to, and that's where you get your positive side. So
The positive and negative terminals are on opposite sides of the wafer.
Yes.
So
That makes a little more sense.
So if you want a daisy chain, you have to chain them top to bottom, bottom to top.
yeah. So more or less they're actually like woven together. You know. I think when I first started out with solar panels, I was kind of confused because it looked like they were all just wired together, right?
Right.
So it looks really simple. If you look at this, it looks like they're all just in one straight line. But then on the back, you can kind of see a little bit better.
But, you know,
They're dipping up to the top every.
They're actually going from one to the other side, like that.
And you could do it where you just tie them all together, top to top and bottom to bottom, but you wind up with a lower voltage and higher current.
Yeah.
So it's kind of like battery technology. If you tie a bunch of batteries in parallel, you get a higher current. If you tie them in series, you get a higher voltage. And solar panels don't generally make a whole lot of voltage, so it's more advantageous to tie them together for a higher voltage and a higher current.
Well, I'll get to that too. So another thing is wattage is It's the term used to describe the amount of work being done in a circuit. And the way that you get wattage is it's voltage multiplied by your amperage. Right? So if you have a 0.5 watt system that's pushing 40 amps, you're only getting about 20 watts. Now, if you have a system it's true, it sounds weird, but it's true. But then if you have like a 120 volt AC line, it's only pushing 2 amps. 2 amps times 320 gives you 240 watts. So it's giving you 240 watts of power at 120 volts for only 2 amps. And
they're inversely proportional.
yeah. And usually, like sometimes you'll see a motor. A motor might be run at a higher voltage, and that'll be to reduce the amount of amperage that it will suck in. So instead of having a wattage that's given at a low voltage and then having to suck in twice as much amperage, you can just give a higher voltage, which is not taking as much power as the amperage, and just give about half as much amperage. So, I don't think I have any pictures of this. So you basically have regular silicon-based solar cells, which are like what we have up here. And then you also have your flexible solar cells. And I've got one example up here. I've got a couple more at home. But any of the flexible cells, they're going to be a lot less voltage and amperage. And that's just sort of due to the chemistry that's being used in them. So like if there's any sort of application that needs a lot more voltage amperage, and you have the ability to have a standalone structure, then you'd probably definitely go with the regular silicon-based alternatives. But if you have like a backpack or something, you're trying to integrate your photovoltaics into, then usually you're going to use your flexible cells.
And the silicon-based cells are generally less expensive too, right, per watt. Flexibles?
Yeah, I'd say so. They're a lot easier to find too.
Yeah.
But like these up here, these I was able to get like from Amazon and then wire them together. But then again, these are not like the professional grade solar cells. These are sort of like, you know, the amateurish
Hobby grade?
Yeah, hobby grade solar cells. Like I think they call them like grade D or something.
Where did those come from?
Amazon. So these are these are normally 3 inches by 6 inches, and the commercial grades are usually a square that's 6 inches squared. And I don't actually have those on that solar panel because that one was probably like semi-amateurish made. You know, I'll show you this. See, it's more of like a half square, I guess. You see that? Yeah. But normally it's going to be like a square for the really professional grade solar cells. And then normally per solar cell you're going to have 0.5 volts and then maybe 4 watts, maybe.
Depending on efficiencies and size and everything else.
Yeah. And I think I can talk about that on the next slide. So, as far as flexible chemistries, you have SIGs, which is copper, indium, gallium, diselenide. And these SIGs, they look sort of just like a flat piece of copper that's been doped with like some sort of chemical.
Perhaps an Indian will get some of that.
And there's amorphous, which is, it looks like a blue shape basically. And I think amorphous is actually silicone as well. But they have like a copper substrate underneath it. So it's sort of like if you shake it really hard, it sounds like tinfoil or something. And then after that, we have organic and dye-sensitized solar cells. And this is something that's really interesting. It's basically just using like regular natural chemicals, not, I guess the right term is natural chemicals. But basically, the idea is like using stuff like lemon juice and putting that into the cell and then attaching electrodes and then basically have your own solar cell. Now,
Things that are less tied to heavy metals on it.
yeah.
Better for the environment. Green on.
Potentially.
Yeah, the concept is basically that these you don't have to worry about. They can, you know, you can dispose of them anywhere. And
I thought as well, the metals you have one of those, the silicone bags with flexibles.
yeah, instead of having to worry about what you're going to do after your solar cells break with
Gallium.
galliums,
Leaching into-
gallium.
And you know, that's selenium, you don't want the selenium.
Yeah,
Yeah, yeah.
you don't want selenium. You don't want gallium.
You don't want any of that.
No, you don't need that.
You don't want it hitting the water table.
No.
Luckily, it's pretty well tied to the silicon, but it's also expensive to produce that way
Yeah.
compared to if you can come up with a good organic.
Organic chemistry is easier.
Here.